Welcome, everybody. Today we are having our next webinar in our series, which is on Gramine, and we have some core members of the Gramine team here with us today. This webinar is being recorded and will be posted to YouTube shortly. And with that, I would like to turn it over to Mona to begin the introduction.
I guess, actually,
The
best laid plans.
So we can all quickly introduce ourselves, maybe. That's probably the best. Okay, so I can go first. I'm Mona Viz, Principal Engineer at Intel Labs, and been part of Gramine project since its inception, and have been collaborating with both Don and Chiache since then. Chiache, you can go next.
Yeah, my name is Jiajie Cai. I'm currently an assistant professor at Texas A&M University. I started off as a PhD student as Don, and I worked for Mona at Intel for a while, and like I've been seeing Gramine, formerly Graphene, from the beginning. Yeah.
So I'll be the first presenter. We'll be doing a team presentation today about the project. So I'm Don Porter from UNC Chapel Hill. And so, this is a talk about protecting unmodified Linux applications using confidential computing. So there are a number of legal disclaimers from Intel, which you can read at your leisure offline. But I want to point out their existence. I'll also note that, as Jiajie has already demonstrated, we recently renamed the project from Graphene to Gramine, and we will likely make this mistake ourselves of calling it one or the other. If you've heard of Graphene before, it is the same project. And this was done in part to avoid conflicts with other awesome projects that also thought Graphene seemed like a good name. So to get started, I need to acknowledge that this is a project that is the result of many people's work, not just ours, although we're the ones that get to stand up and take some credit for it. So I want to take the opportunity to introduce at least some of our major contributors and maintainers, including a team from Intel, including Mona, Dimitri, and Isaku. I'll also note that in general, Intel has made a significant investment in the project. We also have a significant contingent from Invisible Things Lab, including Mihao, Pavel, Voyu, and Boris. You have, of course, me and Jiajie, or the academic arm of the project, and we have several other individual contributors and companies who have been generously helping us get this software where we want it to be. So let's start with confidential computing. And for the purpose of this talk, we'll adopt the definition that I believe as used by the CCC. So confidential computing here is defined as the protection of data in use by performing computation in a hardware-based trusted execution environment. All right, so what does that mean? Or specifically, what is a trusted execution environment? So the details vary. This is still, a relatively new technology that we're all collectively experimenting with. So I'm going to speak first broadly and then specifically. So in broad strokes, the goal of a trusted execution environment is to isolate an execution context for application code from system software, including a host OS kernel or a hypervisor. The idea then is that code and data running inside of this trusted execution environment cannot be accessed or manipulated by anything outside of the TEE. This is particularly salient in the era of cloud computing, where one might want to rent time on machines that are owned and managed by a third-party provider, including a host hypervisor that may not be under the end user's control. But it's also relevant in many other contexts outside of cloud computing. Another key feature for trusted execution environments is the ability to prove to a third party that you're running on the actual hardware you say you are. So in other words, you're not just emulating a TEE, but there's a real TEE that you can trust, as well as the fact that this TEE is running the expected code that you think is there. Pretty much every major hardware vendor is rolling out some sort of TEE support, whether it's Intel, AMD, ARM, etc. And and these things are also not just one, right? So each company also has a few different offerings designed to target different goals, as well as we're all just kind of learning a little bit as we go. This talk will focus on Intel's software guard extensions, or SGX. So in a current SGX, or in a current deployment, when you run an app, say in the cloud, it has an attack surface and trusted computing base that includes not just that application, but the operating system underneath, as well as a virtual machine monitor and the hardware. What Intel SGX provides is a set of ISA extensions that isolate a piece of your application's virtual address space from the rest of system software. And the only part of that trusted computing base, other than what executes inside the TEE, is the hardware itself. SGX uses the term enclave for an instance of one of these isolated environments. You can have multiple enclaves on your system, either in the same app or in multiple apps. What this means for the application developer, however, is that there's now an implementation burden, that if you want to use SGX out of the box, you need to take your application and partition parts of it into an untrusted component and a trusted enclave. For security, the hardware allows you to define specific entry points. So there's the equivalent of a context switch or a system call from untrusted mode into the TEE, right? So you can't just jump to arbitrary points in your code inside of an enclave. And finally, SGX can send a cryptographic fingerprints to third parties to allow for remote attestation, as well as things like secret provisioning. So the thing that you might now be wondering is, well, this all sounds great, but it also sounds like a lot of work to go through and figure out how to partition my application up. And so a natural model that people might want from this is what's been now colloquially called lift and shift. And the idea of lift and shift is that I want to take the entire application and just thunk it down inside of an enclave without dealing with all this partitioning. And this is one of the things that Gramine supports, right? It is this model of lift and shift of an entire unmodified Linux application. So as an overview of the Gramine project, it is a multi-process library OS, or also called a unikernel, and portability framework. The original goal of the project wasn't about confidential computing at all. It's just about taking existing legacy code and running it on multiple different backends. The current backends that we support are Linux and Linux SGX. There are a number of future backends planned, as well as some that are in various stages of completed or maturity. It's a community maintained open source project. The code is on GitHub. It is licensed under the LGPL, and we support cloud deployments using the Azure Kubernetes service. We joined the CCC last fall, and we also were proud to announce our first production ready 1.0 release last October as well. Last week, we released version 1.1, and our plan is to support quarterly releases more or less in the future. In terms of the overall history of the project, this started over 10 years ago when I was a new faculty member at Stony Brook University, and Giage was a new PhD student hoping to, make a splash in the world. And, we all worked pretty hard on this project and published the first paper about it in 2014. And around that time, SGX was starting to get some traction, and Mono, wisely recognized that there was a real opportunity for a portability layer for SGX. And so we teamed up, and in 2017, we published a paper with SGX support and did a code release. About a year later, a group from GoLam and Invisible Things Lab announced a fork. And fortunately, after that, we all got together and decided to pool our efforts to make the best Gramine possible. In September of 2019, we had a sort of poorly numbered version 1.0 that was not production ready under the name Graphene. And we spent the next 2 years actually getting it ready for productization, and then did a release this past year. All right, sorry, we're having a little trouble with the slide advancing here. Anyway, so now we're at the point that we have version 1.1 out, and solutions are in development using Gramine. I'm also happy to report that the community around Gramine is growing, and there is still room for you on the slide. So on the left, we have several major contributors and major institutions that have been putting time and other resources into the project on the left. And on the right, we have a set of, a wide range of different curated applications that we've kicked the tires on, have examples of, or have, some experience firsthand using. And it pleases me that every time I give this talk, that slide gets a little busier. But anyway, we are, of course, always happy to accept help from people who are interested. And with that, I will be happy to hand the floor over to Jiajie.
Okay, thanks for Don's introduction. So next, I will cover the technical part, so essentially the architecture part, and also how would you start with using Gramine. So okay. So as Don has already introduced, the original goals of Gramine is to run a modified application. So what does this mean? So this means, suppose you have a Linux application, and I do have to clarify that here we means the application binary, which is the binary you got either from the Ubuntu repositories, or you have compiled yourself. And so you can take that binary and bring into different kind of platform and run it on top of Gramine. And Gramine is acting as this intermediate layer to sort of support the portability between different platforms. So you can consider, for example, that you can have Gramine running on top of Linux kernel, which is its original setting. Linux kernel could be running on a normal x86 64 platform, or running inside the Intel SGX enclave. So that is basically providing the portability between different hardware setting. And you can also imagine in the future that you can have different kernel, for example, running Gramine on top of BSD kernel. And suppose if this BSD kernel has been running under X5.
Jiajie, sorry to interrupt. I think somehow there is some timing built into the slide. So just watch it. It may move. You can just move it back. Yeah.
No problem. I noticed that as well. Yeah. Yep. No problem. I'll just bring it. Just if you feel this kind of annoying, like bear with me. So basically, like Gramine could be supporting different platform, different kernel, and different architecture using its superior portability support. So how does Gramine does all this? So the main idea of Gramine is to base on what we have a modular architecture. In other words, we break down what kind of operating system components that an application will actually need into several layers. So one of the first layer is called library OS. So the idea of library OS is you basically build an operating system in the user space, not in the kernel, in the user spaces, and as a library. So inside there, we can re-implement a huge amount of system calls, system API, system feature. And so far, there has been 162 Linux system call has been supported out of 325 Linux system calls. Below the Gramine library OS, there is a layer what we call PAL, platform adaptation layers. And the idea of this layer is basically you shrink down whatever system API you're supporting to a very narrow interfaces, essentially what we call a DK calls, or sometimes we call it PAL calls, which is only have 44 calls. So you can see something really large being shrunk down to something really small. And this help with portability, make it really easy to implement this PAL layer for, let's say, Linux or SGXs, and we can just maintain that really thin, small layers to make it portable to the platform we want. And then all these things could be run on top of a real system call interfaces outside of this process. Let it be a Linux system call layers, or if you're supporting your Intel SGXs, you can jump off Enclave and support a system call interface. Okay. All right. So when we're running on all these things Intel SGXs, we actually twisted this module design a little bit. So we separate this PAL layer into two layers. One layer is running inside the Enclave, or we call trusted PAL. And this trusted PAL layer is acting as a trampoline that jump outside of Enclave and interact with another layer, what we call untrusted PAL, to actually make the system call. So you can imagine any kind of system interfaces that is, for example, opening a file, you basically go through a library OSs, access the PAL call, the trusted PALs, or make the open system call as basically Enclave call, go outside of Enclave, go to this untrusted PAL, and untrusted PAL will be the actual one making the open system calls. Okay. So one of the very big benefit of Gramine is to do all these, we have an extremely small code bases. So this code base, a small code base means you have a small trusted computing base, means like when you are either deploying your software, you only have a limited amount of source code that you have to look into and to verify, right? So for example, if you want to support a Redis software here, then what you have to trust is first a library OSs, which is around 25,000 lines of code. And you have Linux PAL, which is 12,000 lines of code, and that's pretty much all, right? And you do not have to trust the Linux kernel and the architecture as well. And plus the Redis, the code base of Redis itself, this could be will be a lot more manageable than a full-fledged virtual machine kind of type of solution to run any application on top of software. Sorry. Yeah, so we are considering this part, essentially the Linux library OS part, plus the trusted PAL inside Enclave as the trusted computing base of Gramine. And of course, is that this is the number we collected so far. This number may change in the future. And of course, this is also not including some third-party dependency if you needed them. For example, we do have to introduce some of the embed TLS's library for encryption purpose, and TLML for reading the manifest files, and UT hashes as the hash functions. Okay. So how do we start with Gramine? So we try to make Gramine as user-friendly as possible using these command line utilities. So first I do have to say, you get a lot of this information, especially updated information, in our official documentations. Our official documentation is great. Like they provide a lot of information, and they also specify there's a few prerequisites you should install. Like for example, including you do have to install Intel SDK and Intel PSW, and also the Intel driver, SGX driver. There are also a few packages you should need to install. And also, so once all is done, like you can start by installing Gramine. So far, Gramine is not yet a part of packages that Ubuntu or Debian has shipped it, but you can with an extract step, you can add our official repository into your apt source, and therefore you can install with apt. So you can simply just install with apt. And once it has installed, you will have to provide a private key. I'm sorry, go back and forth. So provide private key. So what this private key was doing is basically the key that you provided to sign your applications as an enclave. And once they sign it, that will guarantee the integrity of your own application inside the enclave. And once it's done, you can go to our Hello World example and you can play with it. So you should first start with, there's something, a configuration file, what we call a manifest. So what is this exactly is the manifest? So a manifest is essentially a configuration file that specify all the things that you have to trust, including the rules that Gramine should follow and the files that you should be allowed to open, etc. And once you have provided all this information, Gramine could take the information and sign them. So basically, they generate the enclave information and they sign it with the private key you just provided. And then it also generated a token. Usually this generation of token usually happens on the target machines that you are running this SGX enclave. And once it's done, you take the token, you have the signature, you run on the target platform. For example, here you can run. For example, here we have the Hello World program. Know that there are different modes of Gramine. So we mentioned that Gramine so far run on 2 types of hosts. One is Linux mode and one is Linux with SGX. And so with Linux, we call it Gramine Direct. So you can type Gramine Direct Hello World, so which will take the same manifest and runs with this Hello World program. You can also type Gramine SGXs, which will bring Hello World program onto a SGX machines. On the SGX machine you're running and run the Gramine inside SGX enclave. So it's cool in terms of you can switch different modes and test them in different circumstances. Okay, so this is the manifest I just mentioned. So our manifest functions, our manifest file follow the structures of TOML's syntax, and it's basically start with the name of the attributes equals the attributes with the value of attributes. And so you should start with specifying what is the executable that you want to run. Here is Hello World. What are the libraries that you should use to load your other binaries or other libraries? Also, the file system that you need to trust it. So here you can see this kind of look like a container, right? So we kind of take a part of the host file system, push it into the library OSs, and make it become part of the virtual environment that the application has been running. So here we're taking Gramine directories on the host, push it into library OS, and make it into /lib. And of course, there's some SGX's specific attributes. For example, the size of the enclave here, because you would usually specify something big enough, like 1024 megabytes, and number of threads you want inside the enclave. And then you have to list all the files you want to trust. This is extremely important because if someone could simply just modify the files you load into the enclave, it's not safe, right? For example, let's say your binary is Hello World, and someone could actually take the Hello World and modify it. Even other things, for example, like libc. Libc is file being load into the library. If the libc is modified, then you don't have security. So you do have to specify all the files you want to trust, and we'll take this list of file, and we will sign all the signatures and include it in the executions. And they will not be able to be tempered by any attacker. Okay, so we have a Gramine layers that is responsible for shielding your application and the library process against basically a malicious operating system or malicious host outside of the enclave. And this is extremely important. Like, so academically, we usually say this as what we call Iago attack. So there are a lot of attacks that could happen from the host size, and it's extremely hard to defend, mainly because like as an application developers, when you start developing, you don't foresee these risks. For example, when you open a file, you assume, application developer assume that this file you open is safe. But in the world of SGXs, that's not a given. So how do we solve this problem? So essentially, all the security critical path, like for example, like if you want to open a file, that has to be hardened by the library OSs and the trusted layer to against any kind of eavesdropping. For example, if someone could directly look into the argument you are providing or the return value you get from the kernel, that's eavesdropping. Or they can directly attack it. They can take that argument, take that return value, and just change it. And so how do we make sure both the confidentiality and integrities of these system call is extremely important? So we can start with by having all the loaded libraries. So for example, you want to load libc, you want to load libpthread, you want to load any kind of third-party library. You want to make sure all the integrity of these loaded libraries is always verified. And how do you verify it? You verify through, there's a list of valid hash values. And we gather all these hash values when we are assigning our enclave. Next, we also have a file system that's being transparently encrypted. And that is supported through, we have a protected file system. This is a protected file system provided through importing the protected file system of Intel SGX's SDK. And they provide us the protected file. Essentially, these files are naturally encrypted, naturally protected. And once you mount this file system into your system, you don't have to worry about that either being eavesdropped or modified at all. There's also unique cases that Gramine is supporting multi-process, and this is I'll emphasize that not a lot of these portability layer for SGXs could support multi-process. We are one of the first, and also one of the most stable one. And so basically, our system supports when you create a new process. For example, suppose you fork a new process, you essentially create a different enclave, and these two enclaves need to communicate with each other. So the states inside the first enclave will be migrated through the second enclave to the second enclave, so that these two enclaves are on sync. They are considered two processes of the same application. And in that cases, these migrations of the checkpoint is completely transparently encrypted. And also, like, there's all kind of different what we call inter-process communications, right? You can consider, like, if you're a Linux system developer, you know there are pipes, there are IPC messages, there are signaling, there's all kind of different flavors of inter-process communication, and all these things inside Gramine process are all encrypted and protected. And essentially, there are all kind of different additional checks that need to be enforced on all the layers that we suppose to have to reach out around enclave and ask for a host level system features. So you can see, in summary, like, Gramine is essentially this huge effort of trying to create a layer to shield every point when you're trying to reach out to the host for systems feature, because those are the points that you can get attacked by a malicious or compromised host. And of course, we also have, if you consider network communication, we also have SSL TLS protection that you can use to communicate with the remote application that are either also running in Gramine or not inside Gramine, but these connections could be transparently created through our libraries. Okay, let's see. Okay, so one of the cool part of, I'm sorry. Okay. So So Gramine, one of the important part of Gramine is, so Gramine also have a lot of features in terms of providing the SGX infrastructures. Gramine provide SGX attestation. So if you are familiar with SGX has different way of supporting attestation. Attestation is essentially the process of proving that the platform you're running actually had a real Intel CPU, like real good Intel CPU. And also this your application is running inside enclave. And that proof will be given to a remote trusted entity to verify, and that will be verify, and they will be able to trust this platform. And there are two ways. One way is called EPID. Essentially, it has privacy ID. So you actually go to Intel server to verify it. And we also support a more popular form, which is called DCAP, which is called data centers attestations primitive. Yeah, primitive. So essentially now data center, for example, like Amazon's or Google's, they can actually deploy their own server to verify all these attestations. So you don't have to always go back to the Intel's now. So we have that. We have the protected file system, as I just said. This is based on Intel SGX SDK's protected file system. This is put automatically. So if you mount those protected file system into your enclave, they are automatically encrypted and decrypted whenever you read it or write it. And they have integrity protection and confidentiality protections. We also have asynchronous system calls. So if you want to know what it is, so asynchronous system call is a very common optimization for SGX's platform. So mainly because when you're using SGXs, whenever you try to reach out to the host, you have to exit the enclave, and this exit is extremely expensive. So one way to do that is don't exit the enclave. So you can have basically a daemon running outside enclave and do an asynchronous system call where it communicates without doing enclave exits to make the performance a lot better. We have multi-process support, so that includes fork, that includes executes, and all the communication between different processes will be completely encrypted. So that will the host will not be able to compromise a multi-process application running inside multiple enclave. And we also have a Docker integration, and this has become really popular. I think Mona is probably going to cover this part, right? And so we have this automatic container support, where you can take container scripts and generates enclave that could actually run with Gramine. So this is what we call a Gramine shielded container, or GSC. And Mona, should I cover this part too?
No, I can pick up the couple of, I think we have deep dives.
Okay.
So we go back a little
Great.
bit.
Okay.
Sorry, the build is just on a timer or something anyway. Okay.
That's okay.
So let me pick here, Cheche. Yeah, thanks a lot.
No problem.
So Cheche went over several features for SGX support in Gramine. Let me do a little bit deep dive on a couple of these features, and before I jump into the use cases. So as Cheche mentioned, we support two types of attestation, and he sort of explained what attestation is used for. But the nice thing with Gramine is that we support several levels of support. We have this lowest level interface for anyone who actually wants to write their own code to get the hardware attestation and talk to a verifier. We also have a mid-level interface. Basically, anytime you do the attestation to prove to a remote party that you are running in a known good enclave, you have to establish a secure channel. So we have actually done some work in the past where we integrated remote attestation with TLS, and we also provide that integration automatically with Gramine. And interestingly, invariably, when you do the attestation, you establish a secure channel, and then you end up provisioning a secret. That's how most deployments work. So we actually provide that higher level interface as well. where you can actually just specify who your verifier is. Gramine will automatically establish the secure channel, verify and get the secrets provision. The secret provisioning piece, of course, will be workload dependent, but we give you tools to tailored it to your application. And so we already have several examples. And then we already integrate this with AKS, where it integrates with the Azure Kubernetes Services backend. So they already have an attestation backend. They also have a key vault where the keys are stored for any workload that's deployed in Azure. Similarly, we also integrate with yet another backend, which is from a startup called Edgeless, and it's called Marble Run. It's basically a coordinator for when you're running in a Kubernetes environment, and you can configure Marble Run with all the good known measurements of your enclave that you're deploying with Gramine, and then Gramine and Marble Run do the rest. You just bring your workload to run in this environment. So yeah, so we are running both sort of, you can say, in cloud, cloud native environments, and as well as cloud native environments within Marble Run. Cheche also mentioned Docker containers, so let me walk you through that. And in general, we figured while Gramine can run unmodified applications, deployment was challenging because people are deploying their workloads in containers. We didn't want the deployers to go now learn about yet another form of workload running in, say, library OS. So we decided to integrate with containers. The goal was really to automatically secure the Docker containers. You already know how to deploy a Docker container, and can we take the pain out of deploying automatically? The one other part that Cheche went through was that while you don't have to modify your application, you can actually bring an unmodified binary, but you still have to create a manifest. And we also wanted to take the burden out of crafting the manifest. But manifest is really the single most important file you would create, because that's exactly, you don't modify your application, but you have to sort of specify what policies you want Gramine to adhere to. You just specify them, Gramine does the rest. So at a highest level, the flow looks something like this. You can bring an unmodified Docker image. You can optionally give a Gramine manifest, say if you wanted to restrict how many threads you want to run or what the memory size is. But besides that, it's an optional piece. You can run it through our tool. And GSC actually automatically generates a manifest and packages Gramine in the Docker container. The reason GSC can do that is because Docker already does that for us, right? Docker is basically packaging all the dependencies for your application in the image. So we pull all those dependencies in the manifest and allow all of those to be loaded in an enclave. And then all SGX applications need to be signed. So GSC also does that. And then when the Docker run actually runs a Docker image, it thinks it's just a normal Docker image, but when it's launched, Gramine runs first and loads the application. And so in terms of running, this is how it looks like. GSC is very user-friendly. You effectively go pull a Docker image, say you want to run some Python code, and you just run it through our tool where you give it an optional manifest, and it will generate yet another Docker image. And at that point, you can, GSC does actually both of these steps, but roughly at the highest level, you build it, you sign it, and at that point, you again send it to Docker. So Docker would run this Docker container, say you want to run the hello world code, and this code actually is executing inside an enclave automatically. And we actually have tutorials on our GitHub page for experimenting with Gramine. And so with this GSC tool, we make the cloud native support with GSC very, very easy. Effectively, as far as the once you run your Docker container through GSC, it just looks like any other Docker image. So run C sees a Docker image and it runs it, and but the workload is automatically put inside the enclave. Okay, so with all that, now that we have told you what Gramine's architecture and features look like, what can you do with it? And how do you sort of enhance the protections of these unmodified workload? Because running your workload in an enclave is only a small piece of the puzzle. To be able to build this end-to-end solution, you need a little bit more, and Gramine basically gives you all the ingredients to do that. So let me walk you through an example of say enhanced secure machine learning with PyTorch. So if you look at, say, an object detection service running in an untrusted environment, so in this use case, that is desired to support the model IP if you're working with some private models, or if you're operating on user private data. So in an example, if that's the use case you are trying to build, you can actually start with a vanilla PyTorch Docker image. And since I said the owner is worried about the model IP as well as maybe the input data, they will only provide the encrypted images as well as encrypted models. And so by default, if you wanted to support something like this, you will actually have to write additional code to be able to make sure that your code can actually decrypt this encrypted model as well as access the data. But basically, Gramine is taking that pain out. So the user just needs to provide the original Docker image and the minimal manifest. So like I just showed with GSC, we'll be able to create a brand new Docker container. And so when Gramine when this Docker container is launched, Gramine is automatically packaged, and your Docker container application, in this case, the PyTorch application, runs inside an enclave. And so at that point, before actually Gramine can transfer control to the application, it runs this, we call it the pre-loaded code or pre-main, which actually extracts the attestation from the hardware, sends it to a verifier. You have to specify who your verifier is in your manifest. But at that point, Gramine will send the attestation, verifier can verify it, and actually provision some secrets. It could be multiple keys. We show single key in this example, but there is no restriction. And these keys would be the keys to your model and input. And at that point, Gramine will actually transfer control to the application. And then the object detection service runs, and it starts reading the model and the input data. But when it gets the Gramine will automatically decrypt it. The application processes on the clear data, but it's all inside an enclave, so it's protected. Results are created, and those results, before they are sent back to the file system, they are automatically encrypted again. And you can decide if you want to use a different key or the same key. That's part of your secret provisioning modification that you want to do in the beginning. And yeah, and then the results are transferred back. So while I showed you this one example, we believe majority of the use cases can be built using this technique. So yeah, so my plan is to now show you some of the real world use case deployments with Gramine. So as we showed earlier, Gramine supports a large class of workloads, including several databases, web servers, and language runtimes. So we are seeing a huge traction with the AI ML workload, especially in healthcare, financial, and other industries. So let me walk you through some of those examples. Yeah, so first one here is OpenFL. So it's an open source framework for federated learning that allows training machine learning algorithms using data private collaborative learning paradigm of federated learning. So consider a scenario in healthcare where several hospitals want to train a model based on their private patient data. And due to strict HIPAA regulations, these hospitals can't share the data, and that's where federated learning comes into play. So in federated learning, instead of sending the data to the compute, we bring compute to the data. So the data remains private and never leaves the premise, and the model is trained on the local data. So, and at that point, you just sort of send that model back to the aggregator, which aggregates it, and it goes through several rounds to generate the final trained model. So in this example, while the data is protected because it never leaves the premise, there are several attacks that have shown that you can leak the data if you had access to the model, as well as in this model, you also have to make sure that all the hospitals are actually sort of following the rules of the federation is what we like to call it. So that's where SGX or Gramine comes into play, where to protect the integrity of execution on all of these hospital sites, we protect the training part in an enclave, actually both at the aggregator as well as the endpoints. And one other challenge that was posed by federated learning was that each of the hospital, they wanted to make sure, the verifier wanted to make sure that not only they're running the same running the same version of Gramine, but they're also actually using the data they actually originally committed to. But each one ends up with a different hash value because each one is training on different data. Gramine actually provides you tools where you can, given a hash value, you can actually make sense out of that hash value by recreating the hash value based on good known value for Gramine as well as the committed data. So we were able to enable this particular use case much beyond your normal attestation where you're just looking at a blind hash value. We are also giving you tools to be able to make sense out of that hash value. So there are several federated learning projects that are using Gramine. The one I'm showing here is from Intel Labs in collaboration with UPenn's Perlman School of Medicine, where they are securely training brain tumor segmentation models on Intel Ice Lake servers with Gramine. And another one I want to highlight is where several hospitals in Spain are using Gramine in a federated learning scenario for COVID-19 patients. And that is also either under pilot or deployment, going to deployment pretty soon. Okay, and then you can find links for this OpenFL project here. So the second one use case is around model IP protection. So there are several places in the model development and deployment pipeline where a model can be copied or cloned or reverse engineered, and trusted execution with Gramine can enable several of those use cases. So Intel's OpenVINO toolkit now supports, there's a production-ready deployment of OVSA, OpenVINO security add-on that provides tools for model IP protection during model development as well as deployment, and storage and runtime with OpenVINO. So OpenVINO actually integrates encryption and trusted execution protections with model licensing flows to mitigate model theft. So, and it does so by using the Gramine's protected file feature that Cheche just described. And basically, OVSA integrates this with licensing. So before you release the encryption, the model is encrypted, and you sort of verify that you're running in an enclave and present a valid license. And at that point, you get the key provisioned, and then you can run the model. And you could basically, they built this flow very similar to what I showed earlier, using RATLS attestation as well as protected file. And again, you can find a link to the OpenVINO OVSA at the bottom. And last but not the least is a slightly different use case, but still in the AI ML space. This is a joint project that Intel's BigDL team did with SK Telecom. They're applying confidential computing to 5G mobile edge computing offerings. And so BigDL is a unified data analytics and AI platform for distributed machine learning. So BigDL team has developed this product called BigDL PPML, privacy preserving machine learning, where they Gramine is at the heart of that offering. So they've integrated Gramine with this BigDL pipeline, very similar to what I showed you for OpenVINO. So BigDL PPML actually integrates Gramine, but it also offers several other security features such as secure data access, secure gradient and parameter management. And all of those help develop these privacy preserving machine learning use cases, including federated learning. And so yeah, with this BigDL PPML, users can build a secure end-to-end distributed inference service pipeline. So yeah, in this particular work, as I show here in the picture, they actually built showcase several containers protected with Gramine, and sort of they validated the interoperability between them, established secure channels, and showed the whole pipeline working securely end to end. And there's also a link to the paper for this work at the bottom. So yeah, there are, as I just showed, there are tons and tons of use cases. We will see a lot more deployments, production deployments showing up later this year, especially as Gramine has matured a lot. It's enabling quite a few use cases. I already went through the first 3 listed here, which is more around federated learning as well as inferencing. And trusted analytics and AI. BigDL is one platform, but I assume there are several others that are using Gramine. The one that I didn't mention here as much is the work that we are doing more in the research phase in my lab, where we're looking at securing 5G core VNFs with the Ether project, which is also an open source ONF project. And of course, secure databases there are quite a few people experimenting with the databases. We urge you to actually reach out to us if you're using Gramine for your use cases. We have several startups that are building the use cases. Some of them are already listed on our website. And if you would like to be highlighted on our website, we will be happy to do so. And also would like to hear what your use case is. Yeah, Gramine is very actively evolving. We joined CCC in I think September, and that's when we did our first release soon after that. But we did our follow-on release just earlier last week, actually. And this release has several stability improvements for running Rust and Go workloads. Lots of people are experimenting with Go workloads on Gramine. Another one I want to highlight is the muscle C support, which is basically a lighter weight C library. And there are some use cases, especially on the IoT devices, where the TCB size is a concern. So users now have the option of using muscle or glibc. We support both of them. We are constantly improving our testing and validation, and we have the address sanitizers, which really gives us much higher security, finding any security issues before the code is merged. And of course, ongoing several bugs and fixes are going into it. We are constantly enhancing the quality of our code. And quickly, okay, so my build is broken here, but let me quickly walk you through the few future plans. We are planning to publish a new release every quarter, improve tooling and documentation, continue to go through like additional runtimes and workloads. The few that I want to really highlight is now that we have a lot of these workloads covered on CPU side, we are actually adding support for extending Gramine to support arbitrary accelerators, and we're starting with GPU, and this work will be in the process of being upstreamed. And in future, as Gramine has its modular architectures, we plan to support additional runtimes like TDX. And as I mentioned, there's need in the VNF space. We will also be looking at maybe possibly looking at coarse grain partitioning, where you're not really rewriting your application, but coarsely partitioning it for certain use cases like the IO bound applications with DPDK. More on this to come in future. And with that, I would like to wrap up. I know we have very little time left for questions, but we really invite you to join our community. We want to see your workloads deployed or any other contributions you may want to make. And we have the links here in the slide set. Thank you. And maybe we can take a couple of questions from the chat, Don. Oops, yeah. I can't see the chat.
Sure. We have one question that's commenting on whether VM or TDX backends are outside the TCB, and it's one of those things that it's a little tricky, I guess. In practice, this ends up being a little bit split. So there's some amount of work. So we have a Gramine ABI that Gramine is programmed against. And so in as much as that can be implemented outside the TCB, fantastic, right? But in practice, sometimes some amount of supporting work has to be done inside the TCB, perhaps to translate a lower level mechanism into the internal representation. I don't know if Jaji or others want to add to that.
I can also answer this. Yeah. So the just like I showed the VM, in case of Gramine, we are not running a whole full VM. Think of running the unikernel in the TDX, right? So we are sort of building this think of TDX PAL, which is running inside the enclave. So we don't really run a guest OS in that case. We still rely on the host OS, and maybe that will answer the question. We run this, call it the trusted PAL, which is a minimal kernel, unikernel. We're running, in the beginning, we're not thinking of supporting multiple applications. Single application running on Gramine, running inside a TD, which is effectively a virtual machine. But anytime it needs to go to the outside, it will basically use VirtIO interfaces. So we'll expose VirtIO interfaces. We would still use the host file system for any of the usual things. So Gramine is going to be different in that sense when you think about traditional VMs and TDX. No guest OS in that model. We're running a little unikernel. Okay, how one would talk to GPU near TDX and PCI link? Yes, so for the GPU, so with what I mentioned with generic device communication, what we are doing with Gramine is we are giving you a way to talk to a device. We are not securing that link. So this is actually very important to note. With Gramine's manifest, you can enable where we would allow you to open any device, but there is no device DMA. Today, devices don't support DMA, which means your only choice is to use the untrusted memory. So it is application's responsibility to encrypt the workloads and then transfer over. But this is something we are working on at Intel, where we think of it as a software solution. But Gramine actually will allow you to run your whole, say, AI machine learning stack completely unmodified. Think OpenVINO, but it'll allow you to talk to the devices. We have this generic device interface that would allow you to do so. But it's work in progress. It's not fully upstreamed quite yet. How do we know?
There's one more question. Yeah.
Yeah, go ahead. Chechi, you can take that.
Oh, sure. Yeah, I think that's a terrific question. So I think we started by saying that our shielding layers only have to only have to protect a limited amount of the calls. We don't have to protect against all system calls with supports. And based on all these things, we kind of look at them individually, and we do it very carefully. And that's something I pretty much any company could do as well, because we are open source. So you can pretty much look at the source code. Anyone could look at the source code and try to verify it. And that fundamentally go down to, there are a few strategy that you use, either using cryptographics protections, or you just carefully check all the return values on the way back.
And let's see, is there any other question? Did we answer all of them? I think we covered all the questions, correct?
So far, I believe so. Yeah. Yeah. And there was a question about ORAM that I left the messages.
You already answered. Okay, sure. Okay. Yeah, we can hang around a few more minutes if anyone else has any other questions. Yeah, I think in that case, we are good to go. We can then wrap up. Thank you everyone for attending, and we look forward to seeing you on GitHub. Thank you. Bye-bye.
Thank you.